So overall, we've used the steady state approximation to determine the product concentration at any point in time during the course of this reaction. And we've also been able to use fairly simple integrals to come up with this solution. The numerical solution, by not using the steady state approximation, would be more complicated, potentially analytically solvable, but by using the approximation, we end up with that solution in a much less mathematically rigorous manner. So let's look back at the sequential first order reaction mechanism that we saw in the previous video. And now, instead of solving it numerically as we showed in the previous video, let's invoke or implement the steady state approximation and see whether or not we come up with a similar solution. So if we assume that we only have a single reactant as shown, and at time equal to 0, we expect that there's no intermediate or product present. It's only the concentration of A that's present in the system. Now let's apply the steady state approximation and determine what the expected time dependence on the concentration of the product is. So we set up the question in much the same way as we did previously, where we look at the differential rate expressions for each species. So differential rate expression for A, dA dt, is equal to minus K1A. Again, we have the differential rate expression for the intermediate I, and it has both the decay from A to I, as well as the transformation of the decay of I to P. And so the two terms we use to express those two steps is K1A and a minus, because I is being consumed, a minus K2I. And then finally, we have our expression for product formation, which is K2 times the intermediate concentration. So if we apply the steady state approximation to I, we end up with the following expression. So again, by invoking the steady state approximation, we're basically saying that the change in the concentration of I with time is equal to 0. We can equate that to our terms K1A and minus K2I, and we can rearrange for the intermediate concentration. So in doing so, we end up with K1 over K2 times the concentration of A. And like we've seen previously, we can substitute for the concentration of A with the integrated rate law for a first order reaction. Because this is an elementary step, we see the molecularity, it's clearly first order, and so we end up with our concentration of I being equal to the ratio of the rate constants multiplied by that exponential expression, so A naught e to the minus K1t. Now, finally, we can take the concentration of I, substitute that into the differential rate expression for the rate of product formation, which was K2I. We carry out the substitution. We see we have cancellation of the rate constants K2, and we see that the rate of product formation is going to be equal to K1 A naught e to the minus K1t. So now if we integrate this expression, it's going to yield now a very familiar expression for our product concentration, which is something we've seen a few times now. So again, we carry the same type of methodology. We're going to take dt up, any concentration terms down for product, but we don't. We just have the dp. So dp, integral of dp, is just p minus 0. So we end up with the concentration of p on the left-hand side. K1 and A naught, initial concentration of A, those are constants, so they come out front. And we have our exponential term, and the solution for that ends up being, after some simplification, the product concentration being equal to A naught multiplied by 1 minus e to the minus K1t. So this expression for the product concentration, this is identical to what we derived in the limit that the decay of A is the rate determining step in the sequential first order reactions. That was A giving us I and giving us the product. So when K2 is much greater than K1, We saw previously that K1 was the rate determining step, and that's what we are observing under the steady state approximation for the same reaction mechanism. The K1 is the rate determining step for this particular system as well. Only difference is that instead of using a numerical solution or a methodology, we've been able to obtain this exact same solution using the steady state approximation, and I would argue it's a simpler way to determine this particular concentration of product with time. Now, how well does the steady state approximation align with experiment? Well, it does depend on the relative magnitude of the rate constants K1 and K2. And so if we look back at a figure that we presented previously for this particular reaction mechanism, where the reactant A is decaying to an intermediate and P is growing in after the decay of the intermediate 2 product, if we compare the exact solution presented earlier with the solution found by applying the steady state approximation, we see that there is good agreement, although there are some discrepancies or differences that are obvious. So if we take a closer look at this particular figure, if we follow the concentration of A, as shown in our caption, this is identical whether we use the steady state approximation or if we solve for the product concentration numerically. Where there are some discrepancies or differences is with the change in the intermediate concentration. We see that with the steady state approximation, we see that there's slight differences early on in the course of this reaction. We show that the intermediate starts a little bit higher, which we know is not the actual case because in reality, A needs to decay before I can form. And so realistically, the exact solution for the intermediate is shown in the dark blue curve, where we see some growth before we have very good agreement with the steady state approximation. And similarly with product formation, the steady state approximation would assume product forms right away. We know that's not the case because we need to form intermediate before intermediate can be transformed into product. And so again, there's a bit of an induction period, as we call it, or a bit of a lag before we see product formation and the exact solution. But we can see that at longer times, we start to get decent agreement, and definitely by the end of this reaction, we have good agreement with the steady state approximation. So although it's not a perfect solution in every aspect or every time regime, primarily early times, with the exact solution, the steady state approximation does provide, as the term implies, a good approximation or a good sense of how the product concentration is changing with time. And I'll note that this is for a case where K1 is 20 times lower in magnitude than K2. So K2 is larger in magnitude. That was the limit that coincides quite well with the solution that we just showed in the previous slide. And so we need to have a fairly significant, at least one order of magnitude, 20 times is ideal, where the steady state approximation does show good agreement with the exact solution. As those rate constants, as the magnitude of those rate constants become more similar, we're going to see that the exact solution doesn't coincide well with the steady state approximation. And so there, a numerical solution is probably the only way to determine how the change in the product concentration occurs during the course of the reaction, that time dependence on the product concentration. Nonetheless, both the steady state approximation and the limits of the rate determining step approximation, these allow us ways to come up with solutions for the product concentration, the time dependence of that product concentration, for more complex reaction mechanisms that involve more than a single elementary step. So if you have any questions about the steady state approximation, by all means, please send me an email. Thank you.